Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 9, Organic Chemistry 1. In the previous lecture, we talked about the factors that affect the stability of the conjugate base, the negatively charged species. We talked about electronegativity, nature of atom that carry the negative charge, resonance, inductive effect, orbitals hybridization. As an example, we talked about alcohol, ethanol, ejecting H plus to give a conjugate base ethoxide. And we have here propene, alkene. If we took this hydrogen out, it form allylic anion as a conjugate base. And here you have resonance, double bond in here, and then the negative charge would be on that carbon. But which one is more acidic, ethanol or propene? Definitely it is ethanol. Its conjugate base is more stable. The oxygen here carries a negative charge. Here we have negative charge on carbon. Even though it is delocalized over two carbons, this and that, okay, still this is more stable than that one. So factor 1 suggested that the first conjugate base is more stable since oxygen is better to carry negative charge than the carbon. However, factor 2, which talk about resonance, suggests that the second conjugate base is more stable because of the resonance. In general, factor number 1 beats factor number 2. Electronegativity is more senior than the resonance. A negative charge is more stable on one oxygen atom than the two carbon atoms. This periodization will often be helpful, but strict adherence to it can sometimes produce the wrong prediction. Here we have acetylene losing H plus will give the acetylide. Ammonia loses H plus will give amide. Here the carbon carrying the negative charge, here the nitrogen carrying the negative charge. Even though this is more stable than this one. And here the acetylene is more acidic than ammonia. So we can use sodium amide to get hydrogen out of acetylene to form acetylide. Remember from previous lecture, we talked about the equilibrium will go forward to the weaker acid, okay? To the weaker acid. Here we have ammonia pKa 38, and here we have acetylene pKa 25. Which one is weaker acid? Ammonia is weaker acid. It has higher pKa value. Okay. Determine which of the two protons identified below is more acidic, and explain why. In this structure we have OH in here and we have OH in here, and you are asked to identify which one is more acidic. Let's say that this one will lose the H. It will form this anion. The negative charge is on oxygen. The oxygen is adjacent to carbon, carbon carrying 3Cl. Chlorine is electronegative element, so it will have a negative inductive effect. Electron withdrawing group. Electron withdrawing group. ساحب للإلكترونات. Okay? Stabilizing the negative charge. Okay. Let's go to the other side and see if we lose this H. Will form the carboxylate ion. The carboxylate ion can resonate, forming single bond and forming here double bond. Resonance structure. Okay? The resonance will beat the inductive effect. The resonance will beat the inductive effect. So which one do you expect to be more acidic? This one is more acidic, the more acidic. So in general, resonance will beat the induction. Based on this, we predict that conjugate base on the left side A is more stable than B. Therefore, we conclude that the carboxylic acid proton is more acidic. Predict the position of equilibrium in the following equation. We have pyrrolidine 2-on with pK24, and we have the anion of pyridine 2-thione. This anion, okay, as a base. So we have an acid and base. Will give you a conjugate. This will form a conjugate base. This is the acid and this is the conjugate base. So let's see the conjugate base here. Will have the negative charge on the nitrogen. It can resonate to form a double bond in here and single bond in here. So the negative charge will be delocalized over nitrogen and oxygen. Okay? In the thione analog here, it's delocalized over nitrogen and sulfur. So which one is more stable? This anion or that anion? Nitrogen and oxygen, nitrogen and sulfur. Nitrogen is the same in both cases. Now sulfur can stabilize easy negative charge because of its size. So here we have more stable anion. More stable anion. If this is more stable anion, its conjugate acid will be strong acid. If this is more stable, means it's weak base, the acid will be stronger. Indeed, pK is 13. Remember, we have mentioned that the equilibrium will go to the weaker acid. So we are expecting this to go here more than this one. Okay? For each of the following acid-base reaction, place one of the arrow inside the box. Chlorosulfonic acid, or some they call it chlorosulfuric acid, with this anion will go and take this hydrogen, leaving SO3Cl and the chloroacetic acid. pKa here is minus 3.1 and here is 2.85. Of course, this is a stronger acid. Here is weaker acid. The equilibrium will go to weaker acid. Equilibrium will go to this way. Okay. Protonated acetone and Cl minus. Here is an acid. Here is a base. Form a conjugate base and conjugate acid. Now, which is more acidic? Of course, this is a stronger acid, minus 7. Here is minus 2.9. So here is a weaker acid. The equilibrium will go to the weaker acid. Here is acetone acting as an acid, amide as a base. Acetone pKa 26.5 will form a conjugate base acetone anion, and the amide will form the acid ammonia pK 38, and here is 26.5. Which one is a weaker acid? Weaker acid. Okay, so the equilibrium will go to the weaker acid. Draw the structure of the conjugate acid and conjugate base that result from each acid-base reaction. We have this compound has two basic sites, oxygen with lone pair, nitrogen with lone pair. And we have proton donor HCl. Now, which site, oxygen or nitrogen, is more basic character? Oxygen is electronegative element more than nitrogen. So it would like to hold the electrons tight. Okay? So ammonia will be much more easier to attack H, leaving Cl out. So the proton will go to the nitrogen, and this will be the conjugate acid, and Cl will be a conjugate base. Here, we have this compound, we have 2 electrons in here, 2 electrons in here, 2 electrons in here, and again electrons on the oxygen. Which one will be more easier to really react or making a bond with H plus? Okay, nitrogen favor over oxygen, but we have 2 nitrogen. Nitrogen in conjugation with the double bond O, and one is free. These two electrons tied by the electron withdrawing group of the carbonyl. Okay? So this C double bond O is really electron withdrawing this. Okay? And keep these two electrons tied. So this one will attack, and Cl will get out. So we'll have this conjugate acid, and this is the conjugate base. For this compound, we have 3 different nitrogens. Which one will be protonated easier and faster? For this nitrogen, the lone pair are tight because the amine functionality is wholly withdrawing the electrons toward it. For this nitrogen, the same. For that one, this nitrogen, 2 electrons are free to go. So this will be protonated easier. Here is our conjugate acid, and this is our conjugate base. For this one, again, these 2 electrons, this nitrogen, will be tied by the C double bond N. Okay? While these 2 electrons are free. So these 2 electrons will take the H, and this will be our conjugate acid, and this is the conjugate base. Treating the lactone, this lactone, with sodium hydroxide, which initially produce an anion. This is the anion form. That's the initial formed anion. This anion rapidly undergoes an intramolecular proton transfer, in which the negatively charged oxygen atom abstracts the nearby acidic proton. Draw the product of this intramolecular acid-base process, and then identify which side of the equilibrium is favored. Explain your answer. This is the equation, okay? This is a lactone with sodium hydroxide will give this one, okay? Now, as you can see here, you have carboxylic acid group in here, and you have an acidic hydrogen in here. So what do we expect? I'm expecting this hydrogen to leave, forming the carboxylate, and this one will be joining on this oxygen. So what we call it, minus H plus, leaving this, take this out, plus H plus, and this will join another side. So this will be the negative charge, and this will be OH. The carboxylate anion will stabilize by resonance. forming single bond, and here is double bond. So this anion will be more stable anion, and the equilibrium will go shift this way. Okay? We will use a lot of this, the same concept in a lot of chemical reactions. So you have to understand it very well. Determine whether water would be suitable reagent for protonating acetate. We have acetate ion. Can the water protonate that to form the acetic acid and OH minus? Carboxylic acid is a stronger acid than water. So water is a weaker acid, and the equilibrium will go this way. Water will not be able to protonate the carboxylate ion, and if we need to do so, we have to use dilute acid, H3O+. Select the most acidic compound. Amine protonated nitrile. In amine, this nitrogen is sp3 hybridized. For amine, it's sp2. For protonated nitrile, it's sp. And we have mentioned in the previous lecture that as the S character increased, the acidity increased. So here S character is 50%, here is 33, here is 25. And we will find that increasing the acidity in this direction. To be sure of that, let's see the BKA. Here is 38, 31, 14. So this is the highest value and the weaker acid. Identify the more acidic compound. 2,2-dimethyl propanoic acid, acetic acid, or formic acid. Remember, we have talked about the induction, and in a previous lecture we talked about the chloroacetic acid, and if we have chloroacetic acid, here Cl, the chlorine has what we call negative inductive effect, electron withdrawing group, and that will stabilize the conjugate base, decreasing the negative charge on oxygen by pulling it, the electrons toward it. In this example, the other way, this we call the chlorine has negative inductive effect, negative I. The alkyl group R, methyl group, has a different, have a methyl group as a positive inductive effect, pushing the electron away from it, and that will destabilize the conjugate base by pushing electron toward it. So the presence of more alkyl group on the alpha carbon will decrease the acidity because it destabilizes the conjugate base. And pKa here higher than the propanoic acid, higher than acetic, higher than formic acid. So increasing acidity will be this way. Determine whether water would be suitable solvent for the reaction involving sodium amide as a base. If you use sodium amide as a base to run a reaction, you can take the water as a solvent for the media because water will react very fast with amide to form ammonia and hydroxide, what we call it leveling effect. Okay, so it will not really, the base in the medium will not be the amide, it will be the hydroxide. Okay, so water is not suitable solvent for any base stronger than OH minus. The amide ion is destroyed by the water and replaced by hydroxide ion leveling effect in order to work with amide. Then we have to use solvent as liquid ammonia or any solvent with very high pKa like hexane or tetrahydrofuran. Tetrahydrofuran is cyclic ether or even ether, diethyl ether. Okay, no water, should be anhydrous solvents. Lewis acids and bases. A Lewis acid is defined as electron acceptor, while Lewis base is defined as electron donor. In the reaction of HCl with water, HCl will react as acid and water as a base. Water with the lone pair of oxygen will donate this lone pair to the hydrogen, while the hydrogen will leave the chlorine atom, forming base and H3O plus acid. Lewis definition is an expansion of the definition of acid and bases because it includes reagents that would otherwise not be able to classify as acids or bases. Boron trifluoride is accepting lone pair from oxygen, so it is electron acceptor. It is acid. And water again, electron donor base, forming what we call it acid-base adduct. Identify the Lewis acid and Lewis base in the reactions below. Aluminum bromide plus bromine. This is the Lewis structure for aluminum chloride. Bromine Lewis structure. Lone pair from the bromine atom will give the aluminum. So aluminum bromide is Lewis acid, electron acceptor, and the bromine is Lewis base, electron donor. They will form what we call it acid-base adduct or acid-base complex. Here, this adduct can dissociate further to give base, Lewis base, and Lewis acid, giving ammonium ion in the medium, and this is very important reagent. We will learn this in next chapters. Again, boron trifluoride adds Lewis acid. It's accepting from the carbonyl oxygen lone pair 2 electrons, so the carbonyl compound will act as a Lewis base, and boron trifluoride will be the Lewis acid, forming the acid-base adduct. The boron will carry the negative charge, and the oxygen will carry the positive charge, and this can resonate to another form where the positive charge will be on the carbon. So the boron trifluoride really activate the carbonyl carbon from having partially positive to having here a real positive charge. Thanks for watching. See you in the next one.